In this video, we are continuing talking about Bernoulli trials, and we'll do an example in which we have a range of values, and we'll end up tackling this using complements. So the example says, it is estimated that 6% of voters in an upcoming state election are undecided. 15 voters are surveyed at random. What is the probability that more than 4 are undecided? So because this question says that there is a large population, I'm just going to say large pop. So large pop and the fact that it is surveyed at random means we can assume that each person who is surveyed will be independent. Alrighty, so that we are going to end up taking for granted. Okay, so there's two outcomes here for each person. Either they're undecided or they have decided. And that's what's making this thing be a Bernoulli trial. So let's write down the probability that someone is undecided. That's what the question is asking about. So that is 6%, which is 0.06 as a decimal. And that is what we label as P. This is the probability of a success. And the other outcome is the probability that somebody is undecided. Sorry, not undecided. We did that one already. Probability that they are decided. Decided. Okay, so that would be 1 minus P. 1 minus 0.06, which is 0.94. And this probability we can label as Q. This is going to be the probability of a failure. Alrighty, so first, let's do this in one way. I'm going to call this approach 1. And approach 1 is going to be a direct approach. Direct approach. So we are trying to find the probability that there are more than 4 undecided people. So I'm going to write a greater than symbol, greater than 4 undecided members. Okay, and if there's more than 4 undecided voters, that means there can be 5 undecided, or 6 undecided, or 7 undecided, all the way up to 15, because we're surveying 15 people. So we would have to find the probability that there are 5 undecided and add that to the probability that there are 6 undecided, plus the probability of there being 7 undecided, plus ... plus up until probability of 14 undecided, and finally plus the probability of 15 undecided. So we can definitely do this. There would be a bunch of probabilities to compute, and to add up altogether, it turns out there's 11 things we'd have to work out and add up like this. So this would definitely be tedious. Doable, but tedious. I'll put a sad face. So let's tackle this instead by using complements. So that is going to be our second approach. To use complements. So with complements, we want to know, I'm going to leave myself some room here, the probability that there are greater than 4 undecided voters. And when we use a complement, this is going to be equal to something minus something. So what I want you to do is I want you to pause the video for just a minute, just 1 minute, and see if you can determine, well, what are these two things that are being subtracted? Without putting in any numbers or anything like that, I want you to be able to describe what goes here and what goes here in words. That's the true test of, do I understand this on a conceptual level? It can also help guide us to determine what goes in these two spots. What are we going to subtract? So 4, 3, 2, 1, pause it and think about what goes in those spots in words for about a minute. Alrighty, so hopefully you've thought about that for about a minute and tried to write something. Don't worry about if you're right or wrong. It's okay. We'll talk about it together, but believe that the time that you put in to think about things like that is helping. Okay, Let's talk about it together. So I'm going to help visualize this by drawing a Venn diagram. These often help with these complement questions. Okay, so this whole rectangle represents my sample space, which I'll call S. And S, in this scenario, all of my outcomes are all of the selections that we could have of these 15 voters. All right, and I'm going to draw a circle for the set that we care about, and I'm going to label this as A. So our set that we care about involves situations where we have more than 4 undecided voters. And now let's use that to label what the complement would be. So a complement, well, what's the opposite of more than 4 undecided voters? This is where I need to be a little bit careful. It is less than or equal to 4 undecided. So that's somewhere I need to be careful there. If it's not the case, so if I don't want more than 4 undecided voters, that means I want less than or equal to 4 undecided voters. So that's so important that I'm going to make a specific remark about that. So what do I want to be careful about? Well, this, or it's, and by it's I mean this thing, it's the complement, it's not simply less than 4. I need to include the phrase or equal to. Okay. Alrighty. So with that in mind, if I'm trying to count the probability of being in the circle A, so the probability of being in this circle, using our knowledge of complements, that's going to be the probability of being in the whole rectangle, the probability of being in S, minus the probability of being in that complement. And in this case, the complement in words is if we have less than or equal to 4 undecided voters. So when I asked you to pause the video and try to figure out what goes in these spaces, this is what I meant. So before we even put any numbers, it's helpful to describe in words what each thing is. All right, so the probability of S is always 1. There's always the probability of being in the whole sample space, somewhere in the whole sample space, is always going to be 1. So let's keep going. So this equals 1 minus, and now I have to find the probability that we have less than or equal to 4 undecided voters. So there I do have to consider cases, but luckily there's much less cases than we had directly. Let's write them out. So we would have the probability of 0 undecided voters plus the probability of 1 undecided voter plus the probability of 2 undecided voters and the probability of 3 undecided voters plus the probability of 4 undecided voters. So from here, I want you to pause the video one more time for about 2 to 3 minutes, maybe 3 minutes, and see if you can evaluate each of these probabilities. 4, 3, 2, 1, pause it, and see if you can take it from here. Alrighty, so hopefully you've done that. You've paused it for about 3 minutes to try this. I want to just comment that there are much less cases here than in our first approach when we did this directly. And that's often the indicator that using complements is going to be the way to go. Okay, so we have 1 minus, and let's start to work out some of these things. So if we have 0 undecided voters, so let's see, overall, we're serving 15 people. So we'd have 15, and we got to choose 0 of them to be undecided. Okay, and then we're going to multiply that by, it's going to be p to the something. So what was our probability of success? It was 0.06. And in this case, we have 0 undecided voters, so 0 successes. That's going to be my exponent. If there's 0 success, oh, okay, sorry. I'm going to multiply now by the probability of a failure, the probability that someone is a decided voter. We said that was 0.94. Remember, it was 1 minus 0.06. So how many failures would we have? Well, we'd have 15. If 0 people were undecided, that means 15 of them are decided. Okay, so now I can do probability of one undecided person. So I would have 15 choose 1 at the front. That's the number of ways I could pick 1 out of the 15 people to be undecided. Then I multiply by p, 0.6 to the number of successes, which is 1, times q, 0.94 to the number of failures, which is now 14. One thing to keep in mind is if I look at the exponents like 1 and 14, they should always add up to the total number of trials we're doing, which is 15 in this case. All right, so if I continue in this way, I'm going to do the rest of these more quickly. For 2 undecided, it's going to be 15 choose 2 times 0.06 squared times 0.94 to the 13. All right, and then 3 undecided is going to be 15 choose 3 times 0.06 to the 3 times 0.94 to the 12. And then finally 4 undecided will be 15 choose 4 times 0.06 to the 4 successes, times 0.94 to the 11. We'd have 11 failures. All right, let's close the bracket here. So here is where I can use a calculator. I'm just going to go ahead and tell you what we get after we use one. We will end up with 0.0014 if I round this to 4 decimal places. So this is 24 rounded to 4 decimal places. So it's a pretty low probability that something like this were to happen. Finally, in terms of our goals for this section, we finished our last goal. Over the course of the last few videos, we've done examples to see how we can recognize Bernoulli problems and compute probabilities.